Sound check one. Okay, good morning, everybody. As we're waiting just a minute or two for people to log in, get your question. You can ask specific questions from that. You also can ask questions from any of the homework. And if people aren't asking questions, I'll just pick and choose some problems to discuss. So as you're waiting, look through your work, your notes, and see which questions you might need help with, because that would be the best use, I think, of our time. Okay, let's go ahead and get started. One question that I did receive was from Chapter 2, Section 3. I'm actually going, this isn't on the Test 1 review. I'm going to scroll down here and put it at the bottom. So it was item number 2.3.47 in my math lab. And it looks like this. Find the following limit or state that it does not exist. It's the limit as h goes to 0 of the square root of 361 plus h, and then minus 19, all divided by h. All right, so whenever we're calculating limits, what we'd really like to do is to be able to just plug in the value. But we can only do that when the function's actually defined. And in this case, that would give us a 0 in the denominator, so that's not going to work. But whenever you see that you have a binomial, remember by binomial I just mean two terms, and terms are things separated by a plus or minus. So this might not look like what you think of as a binomial, but since these two terms, the square root and the 19, are separated by subtraction, it can fit the pattern of a binomial. We could always multiply, and since one of the terms has a square root, multiplying by the conjugate of that binomial can sometimes be helpful. So that's what I'm going to do. So remember, if you have a binomial a minus b, its conjugate is a plus b. And the reason why that's helpful to multiply by is because it fits the pattern of a difference of squares when you multiply it out. Okay, so in this case, we would have the square root of 361 plus h plus 19 is the conjugate. Conjugate is the same two terms, but with the opposite sign in the middle. And then we can't just multiply it because we want to, but what we can do is multiply by 1. So I'm going to multiply by that value over itself. So I'm not changing the value of the expression, just the way it appears. So now when we multiply these two numerators together, it's going to fit this pattern. So we're going to get this equal to the limit as h goes to 0 of, and then we're going to have the square root of 361 plus h squared minus 19 squared. That's our a squared minus b squared. All right, now this is all going to be over h times the square root of 361 plus h plus 19. And it's usually best to just leave that factored out like that. Don't distribute it through, because what we're hoping is that this h cancels out at some point. By the way, as I'm working, feel free to type any questions about the explanation into the comment section. There's a little bit of a delay between when I speak and when you hear me, so there's a delay in my response, but I will respond. Okay, so now we're going to simplify algebraically. So we have the limit as h goes to 0, and then we're going to have 361 plus h, the square root and the square cancel out, minus 19 squared is 361, and then in the denominator that stays the same. Okay, now 361 minus 361 is 0, so that cancels out. There we go. Having trouble scrolling here. Okay, so we're going to get equals the limit. And by the way, you see how I'm writing limit each time in each step? Oh, so yeah, I have a question here about top chat. Just use top chat. That's what I mean by posting a comment. Yeah. Okay, so we're going to have h over h times all of this stuff in the parentheses. And then we're going to say, oh, okay, well, we have a factor of h divides into a factor of h, so that leaves a factor of 1. So that means we have the limit as h goes to 0 of 1 over square root 361 plus h plus 19. And now, if we were to try to plug in the h equals 0, we would not get undefined. So we can go ahead and do that. We don't need to write the limit anymore. I almost wrote it. But once you plug in, that's the step where you stop writing the limit. You're taking the limit by plugging in. So that's going to be 1 over 19 plus 19, or 1 over 38. Okay, so that was a question that someone sent in, and I also posted the solution to it. I want to show you in your OneNote file. I have a tab for each chapter of Ask My Instructor questions. So it's also posted in chapter 2 under 2.3.47. So whenever you send me an Ask My Instructor question, I file it on here. Okay, in some cases, I'll include a link to a video. In fact, in this case, once this video has been processed, I'll put the link down on this page. In some cases, I just write out the solution. Okay, so going back to our test review page, does anyone have any specific items from the test review that you would like me to go over? Okay, if not, then I'm going to scroll down here and pick ones that I'd like to talk about. All right, so here, number 2 is, unless you ask me about the pre-calculus questions, I'm probably going to focus more on the calculus-oriented questions, maybe a couple of trig questions, because people do have get a little rusty with their trig. Okay, but this one is calculus because it's talking about a limit. And it's testing to see if you know your rules of limits. So instead of giving us the actual functions, they just mention these functions f of x and g of x, and they tell us the values of their limits as x approaches 3. So it turns out that there are our limit laws tell us that if you know the limits of these two functions as x approaches the same value, then you can find the limit of their product, sum, difference, quotient, constant multiple, just by plugging in. So this is going to be the limit as x goes to 3 of f of x minus the limit as x goes to 3 of g of x. We don't actually need to know what f and g are because we know their limits. So this would be 18 minus 5, which is 13. Okay. All right, now this one is an interesting question because it is leading up to something that we're going to be doing in calculus, but it's only using pre-calculus skills. So let's talk about that. So one of the major problems that calculus addresses is the problem of finding the area under a curve. But in pre-calculus, we can find the area under a horizontal line because that area is going to be a rectangle and we have a formula for that. Later on, we're going to be able to find the area under any curve between the function f and the x-axis on a given interval from a to b. But for right now, let's look at what they're asking. Let a of x be the area of the region bounded by the t-axis, and the graph of y equals f of t from t equals 0 to t equals x. So, for example, let's say that we have the x is here. So a of x is representing this value, the area under the curve here, from 0 to x. So consider the given function and graph. So we have f of t is equal to 6. In other words, f is a horizontal line. It's the line y equals 6. So they're just writing that in function notation, f of t equals 6. Okay, so we want to find a of 2. Okay, so a of 2 is referring to, okay, we have our line at 6, and we are going, instead of 0 to some random number x, we're going 0 to 2. And a of 2 is the area under here. So how do we find the area of a rectangle? We just multiply the base times the height. So that's going to be 2 times 6 in this case. Base times height equals 2 times 6, which would be 12. So the area under that curve, or that horizontal line, would be 12 from 0 to 2. Okay, how would we find a of 4? So this represented a of 2. All right, a of 4 is going to be the same diagram. It's just that instead of stopping at 2, we're going all the way out to 4. So we're looking at this area here. So a of 4 is going to be the base, which is 4, times the height, which is 6. So that's going to be, oops, why did I write 12? It's going to be 24. Okay, so there's that one. So then these are really trying to help you think about the problem of a of x representing x greater than 0. How would you represent that function? So since we're looking at 6 being the height of any rectangle we're dealing with, on the interval from 0 to x, what would be the base? Well, that would just be a distance of x units, right? So base times height would be x times 6, or 6x. So your area function for this area would be 6x. So that's all they're asking you to do on that problem. Okay, I just want to remind you, you can always ask questions in the chat bar if you should so desire. All right. Use the continuity of the absolute value function. Okay, so this is definitely a more calculus-based question because we're talking about continuity. So let's just take a step back, and before we work this problem, I want to just make sure everybody understands what we mean by continuity. So recall that for a function to be continuous at a given value c, basically you have no holes, gaps, or jumps. So here would be an example of a function that's continuous at c. Okay, continuous. See how we can just draw the curve right through C without picking our pen up off the page. Some examples of discontinuities would be, for example, you might have a function that has a vertical asymptote at C. And so it might have a limit from the left that's going up to positive infinity and a limit from the right going to negative infinity, something like that. So this would definitely be discontinuous at C. You might have a piecewise defined function, right? So it might look something like this. And this has a gap at C, definitely discontinuous at C. You might just have a hole. So this one is also discontinuous at C. Now it turns out there are 3 conditions that have to be satisfied for continuity, right? So one of them that is violated by both the, let's call this graph A, B, and C here. One of the conditions which is violated by both A and C is that the function has to be defined at C. So number one, f has to be defined at C. So f of C is defined. Okay, so this was not the case in A and C there. Number two, the limit has to exist, or another way of saying it is the limit as x approaches C from the right of f of x has to equal the limit as x approaches C from the left of f of x, which is equal to the limit, the overall limit. Okay, so we do not have that in either A or B. So that fails in A and B there. In A, we have limit from the left is positive infinity, and limit from the right is negative infinity. Any infinity means the limit doesn't exist. In B, the limits do exist. They're going to be whatever y values we have here and here, but they're different y values from the left and from the right, so it fails there as well. C, the limit does exist, but remember, f of C wasn't defined, so it failed that condition. And then the third condition that has to be the case in order for everything to come together and work out is that the function value you found has to be equal to the limit value that you found. Okay, now in order to be continuous on an interval, it has to be continuous, the function has to be continuous at every point on the interval. And we don't want to have to check, when we're asked if where certain functions continuous, there's a limit to how much analysis we can do, right? So what we'd like to do is have whole categories of functions which we kind of understand their behavior, and we can know with confidence where they're continuous. So that's what they're talking about in question 4. They're telling you that the absolute value function is continuous for all values of x. And then they're asking you about this guy here. All right, so what this guy has is a polynomial function inside of an absolute value function. In other words, it's a composition of two kinds of functions. And so one of the things you need to be familiar with when it comes to continuity is that polynomial functions are continuous everywhere. So if the absolute value function is also continuous, then their composition is going to be continuous everywhere too. Okay, so by using that reasoning, simply that we know all polynomial functions are continuous everywhere, we were told the absolute value function is continuous everywhere, and we have a theorem that tells us that means their composition is continuous everywhere. So this function is going to be continuous on negative infinity to infinity. Now, if you're curious what that function would actually look like, and it is good to be able to visualize a function like this one, remember this is a, without the absolute value, it would have been a parabola, which would look, not going to actually find the x values, but let's say that this parabola, which opens upward, let's say it looks something like this. All right, so when you take the absolute value of that function, all it's going to do is it's going to keep all the positive y values the same, and it's going to change any negative y values to positive. So what it's going to do is it's going to keep the parts that were above the x-axis the same, because they were positive, and then it's going to flip those negative values up to positive, reflect that portion of the graph over the x-axis. So you're going to get a function that looks kind of funny, starts to be a parabola, but then it has this little loop, a little lump inside of it there. But you can see it's continuous, right? You can draw it without any taking your pen off of the page, and it's continuous everywhere. Okay, so that's a little discussion of continuity. Any questions about any part of that? Okay. All right, so this one is a calculus question because it's involving limits. It tells us to consider this function, f of x equals x squared minus 289 over x squared minus 17. And they want us to think about the limit as x goes to infinity. All right, so whenever I'm doing limits as x goes to infinity, the way that I like to do it is I think about the highest powers dominate. So you really don't need to look at any of the, when you have a rational function, I should specify that. This only works for polynomial and rational functions. The highest power dominates. So when the x values get large enough, this 289 and this 17 are going to become insignificant to the calculation. So to find the limit as x approaches infinity of this function is the same as finding the limit as x approaches infinity of the terms of highest degree. In this case, that would be x to the fourth over x squared. So that would be the same if we reduce as the limit as x goes to infinity of just x squared. And of course, as x goes to infinity, so does x squared. So that would just be positive infinity. And then for the next problem, limit as x goes to negative infinity, it's still the same function. So I'm going to use the same technique. Limit as x goes to negative infinity of x to the fourth over x squared would be just like finding the limit as x goes to negative infinity of x squared, because x squared goes into x to the fourth, x squared times. And so as x goes to negative infinity, x squared goes to positive infinity, because every time you first x will be negative 1,000,000, and then you square that, you get a positive, what would that be? 1,000 billion? And then, and so on and so forth. So you're just going to keep getting positive values, but very, very large. All right. So what does that tell us about horizontal asymptotes for the function? Well, horizontal asymptote occurs when you take a limit to infinity and you get a constant value. We didn't get a constant value. So there are no horizontal asymptotes for this function. It increases without bound at both ends. In other words, I don't know what this graph looks like exactly, but I do know that at each end of the function, right, I don't know what's going on in here, but at each end of the function, we have increase without bound. So it never settles to be a line, to look like very close to a line. So there's no horizontal asymptote. Now, vertical asymptotes. Let's consider vertical asymptotes. So I'm going to copy the function down and talk about that. So we have f of x equals x to the fourth minus 289 over x squared minus 17. All right, so the function will be undefined anywhere that the denominator is 0, but that may or may not indicate a vertical asymptote. To be sure, you need to reduce the function to lowest terms by factoring. So in this case, f of x is equal to x squared minus 17 times x squared plus 17 in the numerator. And you see how that's a difference of squares. This is x squared squared, and this is 17 squared. So it factors into x squared minus 17, x squared plus 17. Which is convenient because it just so happens the denominator is x squared minus 17. So this is actually equal to x squared plus 17 as long as x squared minus 17 does not equal 0. Oops, lost my place. There we go. Why is that happening? I'm not sure. Here we go. As long as x squared minus 17 is not equal to 0. Or in other words, as long as x does not equal plus or minus the square root of 17. Okay, because at that point the function is defined. But anyway, what this means is that there is no denominator down here that would cause a vertical asymptote. This is over 1. No vertical asymptote. Well, you might say, but wait a minute, what about that square root of 17 and negative square root of 17 that made the original denominator 0? So whenever the factor associated with that 0 can cancel out, it turns out there's just a hole in the graph. So this function is going to look a whole lot like x squared plus 17, right? It's going to look just like x squared plus 17, but it's going to have two little holes in it. So it's going to be a parabola. And over here at negative square root of 17 and positive square root of 17, we have a little hole in the graph where the function is undefined. But other than that, it's defined everywhere, and there are no vertical asymptotes. So again, yes, it's true that we can find vertical asymptotes by setting the denominator equal to 0, but only if the rational function has been reduced to lowest terms first will those actually be asymptotes. Otherwise, they're going to be points where the function is undefined. All right, so in part B, when it asks us to find vertical asymptotes, we know we're not going to have vertical asymptotes. So we're just going to mark this off here. Okay, so any questions so far? Please remember you can type into the top chat box there. All right. All right, so here's another one with a limit, and this one in particular emphasizes the idea that we can calculate a limit of a rational function by reducing if necessary. So in this case, we have the limit as x approaches negative 8 of x squared minus 64 over x plus 8. We would like to be able to, we always check to see if we can just plug in the value and see what the function value is at that point, but we can't because the function is undefined at negative 8. But just like some of the other problems, this factors, this is the limit as x approaches negative 8. It factors in the numerator as x plus 8 times x minus 8 because it's a difference of squares, x squared minus 8 squared. And then in the denominator, we happen to have an x plus 8. That cancels out, so that's nice. So this is going to be the same as the limit as x approaches negative 8 of x minus 8. Now we can plug in, so we go ahead and do that, and we get negative 16. Okay, another concept that's kind of leading up to calculus is secant lines and how they represent an average rate of change. So let's talk about that. So in item number 8, it says a function and an interval of its independent variable. Normally x is the independent variable and y is the dependent variable, but in this case it's going to be the independent variable p and the dependent variable will be v. The endpoints of the interval are associated with the points p and q on the graph of the function. Answer parts A and B. Okay, so it says the volume V of a gas in cubic centimeters is given by V equals 12 over P, where P is the pressure in atmospheres. And so we have two units here, by the way. V is measured in cubic centimeters, and P is measured in atmospheres. And remember they mentioned endpoints of an interval. So here the interval that we're looking at is from 0.5 to 4. And it asks us to sketch a graph of the function and the secant line through P and Q. All a secant line is a line through 2 points on the function. So when you're working in my math lab, one of the downsides is that you can kind of look and work backwards. So what you want to try to do is avoid looking at the answers if you can. Let's see if we can sketch this without looking at what they have. So in order to sketch this, you really only need to recall that you learned in college algebra and or precalculus, y equals 1 over x, the reciprocal function, looks like it has a vertical asymptote at 0. It has a horizontal asymptote at 0. And then there's a piece of it, it's actually a hyperbola if you're familiar with that shape, but there's a piece of it in the first quadrant and there's a piece of it in the third quadrant. It looks like that. Okay, now we're only interested in values of p, the dependent variable, which would be like our x. This would be p and v. Our function, by the way, is 12 over p, which would be like 12 over x, which is just going to be 12 times the reciprocal function. So it's going to have bigger y values. It's stretched vertically, but I'm just going to leave it looking kind of like that because we only need a rough sketch. And we're only interested in p values between 0.5 and 4. So let's see what the corresponding v value would be by plugging into our function. So if we have v equals 12 over p, and if I plug in 0.5, 12 divided by 0.5 is the same as 12 times 2, which is 24. So this graph goes through 0.5, 24. And then if we plug in 4, we have 12 over 4, which is equal to 3. So this would be 4, 3. Okay, and then those are your points P and Q that they referred to in the function. So I'm going to just label them in red, point P, point Q. Okay, and we want to know if we put a secant line through those 2 points. Let me draw in a secant line here. Oop, went to the wrong tab. No, I want this one. There we go. Okay, so we're going to put a secant line through here. All right, then they're asking us, find the slope of the secant line and interpret your answer in terms of average rate of change. Okay, so slope, we know, is equal to rise over run, right? Which is, in this case, the change in the volume, triangle means change, over the change in the pressure. And we can still calculate when we have 2 points, we can still use your y2 minus y1. Well, I guess in this case it would be v2 minus v1 over p2 minus p1. Okay, so let's say we use 24 for our v2, 24 minus 3 over, and we'll have 0.5 minus 4. So that's going to give us 21 divided by 3.5 negative 3.5. So what would that be? 21 divided by negative 3.5 is negative 6. Okay, so this has a slope of negative 6, but remember there are units associated with V and P, right? So V was measured in cubic centimeters. So this was actually 24 cubic centimeters minus 3 cubic centimeters gave us 21 cubic centimeters, centimeters cubed, over, in the denominator we have atmospheres is the unit of measurement. Now, I don't know much about doing experiments with volume and pressure and cubic centimeters and atmospheres, but I do know that those were the units of change. So I can tell you that I can interpret what this function is doing over that interval of time. On average, it's decreasing by 6 cubic centimeters per atmosphere. So in my math lab, they say the slope of the secant line is -6. This means that the number 1, either temperature, pressure, force, or volume, changes at an average rate of blank per blank. Okay, so we're going to say that sorry, 1 second here. We're going to say that the volume changes at an average rate of -6, and then that's going to be cubic centimeters per atmosphere. Okay. All right. Again, stop me if you have any questions. I'm going to continue for a few more minutes. So here's a trig question. I know people get rusty with trig, so I just wanted to go ahead and show you this one. Evaluate the following expression by drawing the unit circle and the appropriate right triangle. So we're looking for the secant of -2 pi over 3. And what does the unit circle have to do with it? Well, we know that on the unit circle, if you look at an angle theta like we have drawn in here, and you look at the corresponding point on the unit circle through which the terminal side of theta goes, the x coordinate is going to be your cosine of theta, and your y coordinate is going to be your sine of theta. Okay, so these are the standard units, special angles, I guess, that we are supposed to memorize. So you can generate this unit circle, these unit circle values yourself. If you just memorize quadrant 1, it repeats in all the other quadrants. The only thing that changes is the signs. The angles are all going to be multiples of these 3 angles in quadrant 1, which are pi over 6 and pi over 4 and pi over 3. Right, so 30 degrees, 45 degrees, and 60 degrees. Remember, pi is 180 degrees. Okay, so what are we being asked to find here? Well, it's got something to do with the angle -2 pi over 3. So negative means instead of going counterclockwise, you go clockwise, right? So -2 pi's over 3. If it's easier for you, think of it as 180 divided by 3 is 60 degrees. To go -2 times that -120 degrees, you're going to go down 60 degrees, -60, and then you're going to keep going 60 more. So that would be -120 degrees, or -2 pi over 3. Okay, you with me so far? All right, so then corresponding to -2 pi over 3, we have x value that is the cosine of -2 pi over 3. And we have a y value that is the sine of -2 pi over 3. So how can that help us to find the secant of -2 pi over 3? Well, we know that the cosine and the secant are reciprocals, right? So the secant of -2 pi over 3 is going to be 1 over the cosine of -2 pi over 3. And we just figured out that the cosine of negative 2 pi over 3 is actually negative 1/2. So 1 over negative 1/2 would be negative 2. Okay, so that's how you use the unit circle to get the value of the trig function of a special angle. So it's really important to get comfortable. If you have forgotten your unit circle, review it. Practice maybe drawing it on your own, like quiz yourself and see if you can get it all right. Okay, moving on. This one has some questions about limits in it, number 10. I've copied the graph over here, but it says use the graph of f to complete parts A through L. If a limit does not exist, explain why. So here we have our graph of f. In part A, it says find f of 1. So in that case, that's not calculus, right? That's college algebra. They're asking you just to find the y coordinate that goes with the x value 1. So you look at the graph and this is the x value. This is the point associated with the x value 1. So that goes through 1, 2. So f of 1 is equal to 2. And then in part B, it asks you to find the limit. I don't know if you can read it. It's kind of small. I'm going to write it over here. The limit as x approaches 1 from the left of f of x. So now we're getting into calculus. So coming in from the left. So here's the left side of x equals 1, right? So coming in from the left, what what y value are we headed towards as we approach the x value 1? Well, this open dot is what we're headed towards. And, oops, I'm on ink to shape and I don't need to be. Okay. And, it has coordinates 1, 1. So that means that the limit as x approaches 1 from the left is going to be 1, the y value. This is we're always looking for the y value, because remember f of x means y. So it's asking when x goes to 1 from the left, what is the y value? All right, and then I'm going to fill that answer in over here. All right, and now moving on to part C, what's the limit as x approaches 1 from the right? So part C, the limit as x approaches 1 from the right of f of x. Well, coming in from the right means we're coming in from this side, but it's still headed towards the point 1, 1. So the answer there is still going to be the y value 1. Okay, now I have another copy of the same function down here so we can keep looking at it. All right, so for part D, then what's the limit as x approaches 1? Well, we already observed that from the left and from the right, this is headed towards the same y value 1. So the limit, the overall limit, must also be 1. Part E, find f of 3. Okay, so f of 3, we're just looking for the y value when x is 3, which looks like it's going to be 1. So f of 3 is 1. And we're going to find the limit next, the limit as x approaches 3 from the left. All right, so I'm going to scroll up a little bit here. The limit as x approaches 3 from the left, we're actually looking at the left side of 3 here. Okay, so coming in towards 3, sometimes people have trouble visualizing this, so I'm going to draw a dashed line. All of this is the x value 3, right? So we're coming in towards that from the left. We're actually going to hit the point 3, 5. Well, we don't actually hit it. We come right up to it and stop because there's an open dot. But that means that the limit as x approaches 3 from the left of f of x is equal to that y value 5. So that's the answer to part F. And I betcha part G will ask us for the limit from the right. Let's see. Yep. Part G then asks us to find the limit as x approaches 3 from the right. Limit as x approaches 3 from the right of f of x. Okay, that's a different story. For that one, we are looking at this side, the left side coming in towards the x value 3, which is actually pointing at the y value 0, right? Because it's pointing at that open dot at 3, 0. I don't know if you can see it very clearly, so I'm gonna erase some of this. Okay, so you see how we have, we're headed towards that open dot. It ends up jumping up to 3, 1, but that's not what we were asked. Limits are not about what happens at the x value, but what happens near it. And near it, it keeps on, its trajectory is to head towards 0. So the limit as x approaches 3 from the right is actually 0. So you can see that the limit from the left, in this particular case, the limit from the left was 5, the limit from the right was 0, and then the actual function value was 1. They were all different. All right, so now it asks, what's the limit as x approaches 3 of the function f of x? The limit as x approaches 3, not from the right or from the left, but just the overall limit. And that's part H. And we would have to say that it does not exist because from the left and from the right, we were headed towards 2 different values. So that would be B. The limit does not exist because the limit from the left doesn't equal the limit from the right. Okay. All right. So I'm not going to do the rest of that problem. There was one more that I definitely would like to do before we stop today, which is simplifying a difference quotient. Sometimes people have issues with this. So let's go ahead and simplify the difference quotient. Now the difference quotient can be given to you in a variety of formats. Sometimes the difference quotient is written like this: f of x minus f of a over x minus a. Sometimes it's written as f of x plus h minus f of x over h. Sometimes it's written as f of x plus delta x minus f of x over delta x. So, but in all of these cases, what this really is just the formula for slope. y2 minus y1 over x2 minus x1. It's just that it's written in function notation. And instead of having an x1 and an x2, we have an a and an x, or a h and x plus h and an x. So we just are labeling the x values differently and using function notation. But this is all about slope. Okay, so the one that they're asking us to work with is f of x minus f of a over x minus a. So I'm going to erase these other ones. And the function that they're giving us is written kind of small here. I'll write it bigger. F of x equals x cubed minus 15x. So we're going to plug in and simplify if possible. So first of all, f of x is just going to be x cubed minus 15x. And f of a is just going to be a cubed minus 15a. So in the numerator, we are going to have x cubed minus 15x minus a cubed minus 15a. But remember that you're subtracting the whole thing, so that negative is going to apply to everything. And then we have over x minus a. Okay, and then we're going to distribute the negative x cubed minus 15x minus a cubed minus or plus 15a over x minus a. Now, really the only way that this is going to simplify is if x minus a somehow divides evenly into it. So what I'm thinking is you could either use long division. If you're going to use long division, you're probably going to want to change the order of the numerator so it starts with x cubed and ends with a cubed. Or I was noticing this is a 4-term polynomial and we could possibly use factoring by grouping, so I'm going to try that. So I'm going to write down the polynomial here, x cubed minus 15x minus a cubed plus 15a. And let's see if we can use some grouping here. So, for example, I don't want to leave it paired this way, because if you factor out, say, an x here, that leaves x squared minus 15. Negative a would leave a squared minus 15, and these don't match up, so then the grouping fails. So I'm going to rearrange this. I noticed that if I put the 15x and 15a together, that could result in an x minus a being left behind when I take out a negative 15. And then also x cubed minus a cubed, that's a difference of cubes, which can actually be factored. Remember that the formula for a cubed, factoring a cubed minus b cubed, is a minus b times a squared plus ab minus b squared. Whoops. Okay, so we could use that formula, and this is going to factor into x minus a times x squared plus xa, or ax, plus a squared. And then that was the first pair here. And then if I factor a negative 15 out, we're going to leave behind an x minus a there. So now these two terms have an x minus a in common, right? These are two big terms that are separated by this minus. We can factor the x minus a out front. And that's going to leave behind the x squared plus xa plus a squared. Oop, that's a little sloppy. Let's fix that. X squared plus xa plus a squared. And then the minus 15. Okay, so I'm going to put that, I'm going to use that. I'm going to write my numerator as x minus a times x squared plus xa plus a squared minus 15 all over x minus a. And then that will cancel. And you're left with x squared plus xa plus a squared minus 15. So that's the simplified difference quotient. All right. So that's all that I'm going to do for today. Remember, you can always send me your Ask My Instructor questions. I'm happy to receive them, and I will be posting them right here in the OneNote folder, which is where you can also find the practice test. Thank you for attending today. If you found this session helpful, or if you're watching the recorded version and you found it helpful, please give the video a thumbs up. That helps other students to find the video.